So we call this one the spring and block problem, and in essence, what it implies here is that this block was pushed back against this spring and then released, and then slides to a stop somewhere over here. So this is a rough surface with coefficient of friction mu. The compression distance of the spring is x. The spring constant of the spring is k. And then if it slides to a stop, it's d. But the first part of the question asks, what is the acceleration of the block at the moment that it's released? So basically it says, you push it back here and you let it go. So the moment it's released, some things are still happening. One, the spring is completely compressed and the speed of the block is 0. So if we look at a force diagram for the block at that moment, we know that the earth is pulling it down, call that the weight, we use mg to represent that. There's some normal force here, that's the perpendicular force by the surface, and the spring is pushing the block to the right, and we call that Fs, the spring force, and we know it's equal to kx. And so if we want to figure out the acceleration is, we know acceleration is equal to the net unbalanced force over the mass. So in this case, the way we've drawn this out, the acceleration is equal to the force by the spring, that's kx over m. Now, the way this problem is drawn up, it implies that there's no friction there. We actually know that there's probably some friction there, but for simplicity, we ignored the frictional force there, and we just got the acceleration caused by the spring. The next question says, how far along would this slide before coming to a stop? So in essence, if you push the spring back a distance x and you let it go, it's going to start to slide, and it's going to slide all the way and come to a stop here. So what we're doing is we're looking for d. So what does that mean? Well, what do we know? We know that if you push it back against here, all the energy is in the spring, and then when you release it, it slides and all the energy is released to the surroundings. So we have representations for these. So we say that the initial energy has to be equal to the final energy. So when we look at that as an idea, all the initial energy is in the spring, and all the final energy is the energy that's released to the surroundings. So we call that the work done by friction. Now, what does that mean there? In a general sense, we know that work, if the force is constant, is equal to the force times the distance that the object moves while subjected to the force. No big deal. If we look at this block as it's sliding to the right over this rough surface, so here's your block, it's sliding to the right over this rough surface, the forces on it while it's sliding are the same mg, the same normal force, but now the force is the frictional force between the block and the surface. So what do we know about that? Well, we know that to get the frictional force, it's equal to mu times the normal force. But what do you notice about the normal force and the weight? Those are equal, so this is mu mg. And so if work is equal to force times distance, the work done by friction should be equal to the frictional force times the slide distance. And if I substitute that in here, it's mu mg d. So we know that the spring energy is 1/2 kx squared. And according to what we derived down here, the work done by friction is equal to mu mgd in this case. And this is a true case as long as your surface is flat. So in general, if your force is constant, it's Fd. But this mu mgd is for a flat surface. And so now, let's see if we have everything we need to solve. We're given k, we're given x, we're given mu, m, and we know the g, and so we can solve for d. Not too hard. The next part of this problem is interesting because it asks, as you watch this slide a certain amount, it wants to know, like, how far has the block traveled given a new speed? So it says here, well, let's say that the block is still slowing to a stop over here, some speed v this direction. It wants to know, how far do you think it slid given this new speed? So we can use the same conceptual framework for this, where we know that the initial energy has to be equal to the final energy. The initial energy is still all in the spring, but the final energy this time is the kinetic energy plus the work done by friction while it's sliding to get to this amount of kinetic energy. So when we plug and chug this, we end up with 1/2 kx squared is equal to 1/2 mv squared plus mu mg, and this is this d here. Not the full d that we had before, but obviously it slid less if it's still moving. So this d here is this d right here. The last question, I think, is actually the hard one. And the last question says, as this spring uncompresses, a certain amount, while the block is still being pushed by the spring, but it's still moved a certain distance, let's say it's here now. So the spring is actually uncompressing a certain amount. So let's say it's slid this distance d here. This is a new d. It wants to know what is the speed of the block when it's moved this distance d here. So I find that this one's a little bit more challenging, but we start with the same conceptual framework where we know that the initial energy has to be equal to the final energy. So the initial energy again is all spring energy. The final energy though, the spring is still partially compressed, so it has some spring energy in it. It's moving, so it has some kinetic energy. And it slid over a rough surface, so we've lost some energy to the surroundings in terms of the work done by friction. So this is a little bit more complicated than the last one, but I think we'll still have everything we need. So this is 1/2 kx squared, that's the spring energy, and it's equal to 1/2 k. Now, this is the hard part because the equation is 1/2 kx squared, but what is this value here? Well, if the initial compression was all x and it slid a distance d, the amount that the spring is compressed left with is x minus d squared. So this is the energy that's left in the spring plus 1/2, just kidding, mv squared for the kinetic energy plus mu mg, and this is d, the amount that the block is sliding while it's uncompressing. And now I think we're good to go. I think we have everything we need, so let's check. We know the spring constant and the initial compression. We know the spring constant, and if we know the initial compression and the amount that it uncompressed, we got those. We know the mass. We know the coefficient of friction, the mass, the gravitational field strength, and the amount that it slid. And so the only thing we're left with is the speed, and you can solve. And that's it.